It's my great pleasure to introduce the last speaker, Stefano Boccaletti. So it's a good friend, great scientist. He's professor in Italy, in Florence, CNR. Is editor-in-chief of a great journal called Solitons and Fractals, where you can see many papers on this topic of networks. In fact, however, the title of the journal is very wide in scope. So Stefano is, as I said, for a long time works on this area of complex networks, but especially in synchronization and chaos, where he's a great specialist. And today he will talk about things of synchronization, I think, in hypergraphs and simplicial complexes. So, Stefan.
Thank you a lot, Jose, and thank to the organizer for their effort. It was, while I'm sharing my screen, I have to tell you that people in Moscow really put a lot of effort to allow us to have this meeting, and it was not so easy, and it had a lot of problems, you know, for the pandemics. I hope the next time very soon to be able to come. Do you see my screen?
Yes.
Yes. So I go ahead, and I want today to concentrate because many other talks before already introduced the idea of higher order interactions in a network, you know, the idea of hyperedges, simplicial complexes, and so on and so forth. So I want to describe today possibly the most elegant result that is available on synchronization, which is the master stability function. Master stability function is really a tool, a completely rigorous tool, which assess the necessary conditions for having a network, a population to synchronize. And now I want to show you how to extend this technique to the case of p-uniform hypergraph and to the case of simplicial complexes. That is, we imagine to have a sort of a population of dynamical units and interactions between this among these dynamical units, which are described by p-uniform hypergraphs and or simplicial complexes. Why we speak about synchronization, let me just tell you, because synchronization is, as I said, the emergence of a collective states in a population, and it's really relevant in many circumstances. For example, the photo you see is a tree, and which is populated by fireflies, which during the night, in order to attract females, they're flashing in unison, and they're producing a sort of Christmas tree, you know, effect, so that the tree becomes completely illuminated, and it's really a beautiful effect. But together with this, you know, you have pacemaker cells in the heart, so synchronization is extremely important there to ensure the right functioning of the heart, and oscillating chemical reactions. It is known that stock markets synchronize. There is synchronous clapping of audience, synchronization of networks of coupling sensors, and then experiments with lasers, electronic circuits, power grids. I mean, there is a huge quantity of system. If you want to know something about synchronization, I mean, we just recently published a quite comprehensive book, which is at the end of this slide. Okay. So let me pass the first 2-3 minutes to describe you the original master stability function approach, and then I will move to the extension. So in the master stability function, what you imagine is that you have a population of n identical oscillators or systems. That doesn't matter if they are oscillators. These systems are represented by vectors, state vectors xi, which have m variables, so they belong to Rm, and a vector flow f. That is, in absence of any interaction, each of such oscillators will evolve with this vector flow. And obviously, the flow is a function from Rn to Rn, and so on, so forth. And now you couple them, that is, you put here a coupling strength sigma, then you couple them by means of an output function H, and by means of a network adjacent symmetrics Aij. So here we are still in the case of pairwise interactions. Okay, so here you have three ingredients. One is F, the evolution of the isolated system. One is H, the function H tells you how a system interact with the other, and A, which is how the systems are coupled. So the F and H are pertinent to the dynamics, so they describe dynamics. A is pertinent to the topology, describes how the nodes are interacting. So one way of screening, you can immediately see that you can introduce the Laplacian matrix here. Laplacian matrix is symmetric, has it's zero-row sum, so it has this property. And being symmetric and zero-row sum, this means that the solution, the synchronization solution, which is x1 equal to x2 is equal to xn, is always present, exists, because when you plug here the synchronization solution, this term here identically vanish. Not only is present, but is invariant. It means that for whatever value of sigma, the solution is the same. And now you want to study the stability of the solution. That is, if you really see this solution. Okay, so if you want to study stability, one usually considers perturbations. That is, you consider these vectors delta xi, how much node I is far away from the synchronization solution. You write the linearized equation for such elements, which is nothing but putting Jacobians to the function f here, Jacobians to the function h here, calculate this Jacobian on the synchronization solution and applying to delta xi. And then you consider in block form, because this is for each oscillator I, so in block form, you take a huge, big delta x error vector, which has the first m component are delta x1, the second m component are delta x2, the last m component are delta xn, and you can write the equation in this form. No? The identity n direct product with jf minus sigma Laplacian direct product with jh delta x. So this is the equation of evolution of the vector. That is how you are distant from the synchronization solution. And now the important point here is that the L is a zero-row sum. And symmetric matrices, being symmetric is also always diagonalizable, and the eigenvector forms a basis of Rn, and being zero-row sum, the first eigenvalue lambda 1 is 0. Moreover, all the eigenvalues are real, so you can order them in size, lambda 1, lambda 2, which is the second smallest, lambda 3, lambda 4, lambda n being the largest. And so the first eigenvalue is 0, and the associated eigenvector is this one. You see, in this eigenvector, you have all components are the same. That is, this eigenvector is pointing in the direction of the synchronization manifold. And since now the eigenvectors are forming a basis, it means that all the other eigenvectors, from the one associated with lambda 2 to the one associated with lambda n, are forming a basis for the transverse space with respect to such manifold. Therefore, what I have to do is I have to project my error vector into this basis of eigenvectors, which are the ones which are diagonalizing the Laplacian. And I write, therefore, this vector has a linear combination of these eigenvectors times some the vector Xi, project everything, and write equation for each eigenmode Xi. So you see the equations are these, and now you notice another important characteristic of these systems, that if you take the coefficient Xi and the coefficient Xi prime, the only difference in the equation is the value of the corresponding eigenvalue. So in one case you have here lambda I, and the other case you would have lambda I prime. So the genial idea of Lupercora was, let's consider this equation and let's parameterize this equation. That is, let's substitute sigma lambda with a parameter nu. And let's, as a function of nu, calculate the maximum Lyapunov exponent of this linearized equation when fed with the synchronization solution. So you have basically one single solution, nonlinear equation, which gives you the solution S. Then you have a single linear parametric equation, which for each value of nu gives you the maximum Lyapunov exponent. And the idea is exactly this. So I have here nu, I have here the maximum Lyapunov exponent, and each possible network is a series of points here, because this nu is lambda sigma. So you give me a network, I go to the Laplacian, I see the spectrum of the Laplacian, of eigenvalues of the Laplacian, and this spectrum is located in some position in this axis. So if I study this function, I study the stability of the synchronization manifold for all possible networks. That's why it's called a master stability function. So, and now you realize immediately that you give me F, that is, you give me the system, Rösler, Lorentz, whatever. You give me H, you give me how the system interacts, and I immediately calculate this function, and I can have only three possibilities. Now, the value of the function at lambda equal to 0, that is at nu equal to 0, must be the maximum Lyapunov exponent of the system itself, of the isolated system. So if it is chaotic, it will be something positive. So my curve will start from a positive value. And then I can have a curve which is either monotonically decreasing, which is called a class 1, or monotonically increasing, class 3, or V-shaped. In one case, I have only one intersection here with a new axis. So it means that I can always synchronize here because it's sufficient. Lambda 1 is 0. It's sufficient that I put lambda 2 times the sigma on the right of this. And then all the other eigenvalue will be placed here. So they will correspond to directions which are indeed stable, contractive. And therefore, I have the entire tangent space to the manifold of synchronization will be contractive. In the case instead of class 3, I can immediately say this system, this specific system, I will not synchronize. No matter how I construct the network of interaction, my eigenvalues will always stay here, so it will always correspond to positive values in the tangent space. So my synchronization will be always unstable. And instead, in class 2, what I have is that I have to position the network times the spectrum of my Laplacian times sigma in a finite region here, because I can have here instabilities for larger eigenvalues and instabilities here for smaller eigenvalues. So I have to compact my spectrum. So master stability function is very elegant, as you see. In a single function, I give you all possible networks. And I can immediately make prediction on the threshold, synchronization threshold, and I could stay speaking here at least 2 hours saying how many predictions you can make with this function. Actually, you can make many more than just simply calculating the threshold for synchronization. So we started from here, and we wanted now to see the case in which you are not limited to pairwise interaction, but you consider many more, many more interactions. So let's start with P uniform hypergraphs. You have now n nodes. And now you have, we start for the case P equal to 3 for the beginning, and then I show you how this can be extended. So now you have this equation, and the only difference that you have before is that you have a coupling function h of xi, xj, xk, and a tensor t, ijk with a double sum. So here is a group of P uniform hypergraphs, and the tensor is a tensor whose elements are 0 when the 3 nodes are not having an hypergraph, and 1 when there is an hypergraph connecting the 3 nodes. Again, this is exactly the same. And now the trick is to consider, as before, functions, this h, which are synchronization non-invasive. That is, functions such that when you calculate a function in x66, are 0. So this means that h of x66, when everything is synchronized, is 0. And this guarantee, again, that when you are synchronized, this is vanishing, you have a manifold, the manifold is invariant with respect to sigma. Okay, so the existence is guaranteed. And now let me make an example. Let me go back to the case of diffusiveness. So we suppose this 3-body function is a diffusive-like function. That is, this h, xi, xj, xk can be written like some h tilde xj, xk minus h tilde xi, xi. It's a sort of diffusion on top of a triangular structure. Okay? When you do this, you can easily show that you can introduce this delta I, which is nothing but the generalized degree of the node I, exactly as introduced by Karin a few minutes ago. You can introduce the Laplacian tensor L, whose elements are T, I, J, K minus 2 delta I. So you have in the diagonal now of a tensor, you have this quantity. You can rewrite the equation this way. You can consider again the delta xi, the error vector from the synchronization manifold. And now when you calculate the Jacobian, you have to calculate the Jacobian of f in xs. It's the same, but when you calculate the Jacobian in h, you have a first part in which you differentiate with respect to xj times delta xj, plus the second part in which you differentiate with respect to xk times delta xk. And now, for simplicity of notation, let me introduce this J1 and J2. So J1 is the first part of the Jacobian in which derivation is done with respect to the first variables, and J2 is the one with respect to the second variable. And you make plug there, you make a little bit of some, calculation, especially you notice that some elements here does not depend on k, so you can bring out of the sum and few tricks, and at the end you exit with this nice equation, which is that delta xi is jf xs delta xi plus, now it's, you see, a single sum, so you are back in a matricial representation. You can do this because of the property of the Laplacian tensor. And you have introduced this tau, which is a matrix, in which the elements for I different than j is delta ij, and the element, so it's the generalized degree of the link ij, and this is minus 2 delta I, the generalized degree of the node I. So exactly the two quantities that Karin has introduced just a few minutes ago. Now, this is a sort of generalized Laplacian. I will then generalize for every kind of P. And again, it's a zero-row sum matrix. So once again, you can take the diagonalization of this matrix. You will have a basis. You will now project the error vector into this basis. You will get, again, a parametric equation where here you have sigma lambda, but this lambda, the variance is that this lambda is the lambda of this matrix tau, not the lambda of the Laplacian, okay? Sorry. And once again, you give me F and H, and there will be the three classes, class 1, class 2, class 3. So immediately I can tell you how is the structure for all possible structure of triangles in this case, which one can synchronize, which one cannot synchronize. So the difference with the case of the classical matrix, now the classes are calculated with explicit dependence to this double Jacobian, and the stability has to be checked with the eigenvalues of the matrix tau. What happens when we go to generic p-uniform hypergraph? When you have generic p-uniform hypergraph, you again make the diffusive hypothesis. I repeat that you can also get rid of such hypotheses. Actually, in the Nature communication that we just published on this, we demonstrate also the case in which not necessarily you have to go through a diffusive-like equation. But since it's much easier to explain, I use again the same approximation. So you will have now a coupling function which depends on p variables. So it will be function xi, xj1, xj2, xj p minus 1. And you imagine that this is h tilde of j1, jp minus 1 minus h tilde of xi, 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 xi. And the key point is that now you define a generalized Laplacian matrix, LP, and the elements of this matrix are 0 if there is no link. That is, if the corresponding element of the adjacency matrix is 0. Is delta ijp when there is a link, so when the corresponding element of the adjacency matrix is 1, and this delta ij is the p degree of the link ij, that is the number of p-uniform hypergraphs which are formed by the link between node I and node j. And then in the diagonal elements, you have minus p minus 1 factorial times delta ip, where the ip is again the p degree of node I, the number of p-uniform hypergraphs which are having inside node I as a vertex. When you do like this, believe me, calculations are a little bit, you notice that for p equal to 2, you have L2, which is exactly the Laplacian, because you have 0 if there is no link. How many links are formed by the link ij? 1. So you have 1 when there is the link, and here you have 2 minus 1, 1, the degree of the node. Okay? So, but this generalizes the Laplacian. It's a way of writing the Laplacian matrices for all possible hypergraphs of dimension p. When you do like this, and you consider now, when you consider now stuff, you can show that this Laplacian is exactly the one you have to diagonalize. And you find again for p-uniform hypergraph of whatever dimension, the same 3 classes of the master stability function. And now let's go to simplicial complexes. Again, I limit myself to links and triangles, but then I will show you that you can generalize for all kind of triangle. Now you have therefore a population of dynamical units which are evolving following their internal rules f plus 1 first term which accounts for pairwise interaction, a second term which accounts for 3-body interactions, and in general you can have many more. Here what you do, you write delta xi, and then you will have here the Laplacian L2 times jg plus the Laplacian L3 times j1, j2, like we just have shown. And now the big point is that this Laplacian here and this Laplacian there are both zero-row sum matrices. Okay, so if you want to simplify notation, you denote, you simplify, and you write this in block form. Okay, again. And now you have these 2 matrices, lambda L2, L3. They're both zero-sum matrix, so they both contain lambda 1 equal to 0 as an eigenvalue, and the corresponding eigenvector which points to the synchronization manifold. But they not in general they don't commute. So it means that the eigenvector from V2 to Vn of the Laplacian L2 are forming a basis of the tangent space. On the other hand, also the eigenvector V2 Vn of L3 is forming a basis of the same space, but the two bases are different. So since they do not commute, the eigenvectors are different. So since the eigenvectors are different, the idea is we refer to one set of eigenvectors. Okay, for example, we can choose the eigenvectors as usual of the Laplacian L2. We expand the vector on this set of eigenvector, and we map the basis of which diagonalizes the other matrix on this basis. So you will have a unitary transformation because you have here something which will be complete. Since this is diagonalizable, this part of the equation will be, of course, variational. But this other part takes into account the fact that the L3 is not diagonalized by the same eigenvector. However, since it is diagonalizable, and there is another basis which is also orthonormal, there will be always a unitary transformation from one basis to the other basis. So you make a little bit of algebra. It's a little bit, so to say, cumbersome, especially you have to stay careful not to lose notation, sign, and something. And after doing this calculation 3 times, you get the following. So you get one single equation which is nonlinear, which gives you the synchronized solution. And here a system of n-1 equation for the projection of the vector on all possible on a given basis of the transverse, so to say, manifold, which are however coupled. That is, in the equation for eta I, there is all other possible eta j multiplied by the corresponding transformation coefficients, okay, from one matrix to the other. But still, this is everything which is done once you have the structure of the L2 and L3. This is simply calculating the mapping of one basis to the other basis. So the problem has been reduced to m-dimensional nonlinear equation for the synchronization state, coupled with a system of n-1 linear yet time-dependent equation. The maximum Lyapunov exponent ratio can be calculated in the sigma 1, sigma 2 plane. And again, you have 3 classes. You have a class in which there's no stable region in the plane for no whatever coupling strength you can synchronize. A class in which you see the coupling region has an infinite volume, it's infinite in the plane, so after a given while, you always synchronize, and a situation in which you have a region which is bounded in the plane, and so you synchronize only inside this region. Here are a few examples of simplicial complexes. Here, for example, you have 2 triangles and a link, in which we implement the Rosler oscillator, and we have shown that indeed the synchronization error is 0, so you have black here in the plane, exactly on the limit where the master stability function assume pass from positive to negative. Now this, you see, it's a problem because you cannot factorize and put together in a single function. You have to consider that this is a couplet system. The same, if you take any order, the procedure is the following. You select one of the P generalized Laplacian eigenvector set. You map all the other eigenvector set into the one you have chosen, and you get an m-dimensional nonlinear equation for the synchronization state coupled with a system of n-1 linear equation because each one of the functions that are representing many-body interaction will be mapped with the corresponding unitary coefficients that map the basis into the basis of the Laplacian you have selected. So you can always select, for example, the classical Laplacian and map all the other generalized Laplacian into the original one. Now, again, this is good because you have solved here the most general case, but it's not so elegant because you don't have a function. Now, in order to have a function, you have to have some specific property. I mean, not always you have a function, but there are situations in which you do have a function. And you do have a function, you see, for example, when your interacting function are not only diffusive-like, but they are natural. What does it mean, natural? This is diffusive, so it means that the pairwise function is a diffusion and the three-body function is a diffusion. But in addition, you have to have a condition of natural coupling. The condition of natural coupling tells you that the function h, which is the one regulating, so to say, h2, the three-body interaction, when you are in the synchronization manifold, is equal to h1 of x. So this means that this is a coupling function such that when you are in the synchronization manifold, you see the other two nodes as a single node. Okay? This means natural coupling. And it's expressed by this condition. When you have this condition, this simplifies enormously because now the Laplacians here can be summed term by term. And so now you have sigma 1 Lij1 plus sigma 2 Lij2. And therefore here you can define a unique matrix, which is called the effective matrix, M, which is a L1, the original Laplacian, plus R L2, well, L2 is the generalized Laplacian for three-body interaction, with this R being the ratio of the corresponding coupling strength. And now this M is also zero-row sum matrix because it's the sum of two zero-row sum matrices. And therefore now we can diagonalize with respect to this one matrix, the effective matrix. And when you do this, you eventually end up now with, again, a unique function, a parametric single parametric variational equation for the projection of the vector, and from which you can extract a maximum Lyapunov exponent. Okay? And now you see the only difference is that now once this projection has been done not with neither with the original Laplacian nor with the three-body Laplacian, but with a combination, with effective combination of them. And now I show you a few things. For example, this is the master stability function in simplicial complexes for Lorentz system, and you see you have all classes. Then you have for Rössler system. Here is for Rössler system, and you see here you have all possible coupling. You see here is Rössler system coupling through the first variable with xj square xk, or with yj square yk, or with zj square zk. Here is coupled with the second variable. Here is coupled in the third variable, and you have the function f is the same, but there are different function h. You have all possible, master stability function here, and in Lorentz the same. Here you have also a nice function. You have something that you didn't see before. Not one region of stability, but one and another region of stability. So this situation is a situation which, if you prepare the system here and you start increasing the coupling strength, you first synchronize, then you desynchronize, then you resynchronize. So it's something nice. I mean, I never saw something of this style, that you increase the coupling strength, you synchronize, desynchronize, and resynchronize. Another thing that is very important to say is that what I told you has sense only if the coupling function are nonlinear. Because if the coupling function are linear, you can always write them as the sum on the three. For example, if a coupling function of three body is linear, you can always write them as the sum of function in each link. So you go back to the classical, network case. To have a simplicial complex interaction, you really need a nonlinear function as it is here. And then finally, we prove in the Zachary club, again, the general case. And also it works on real-world network. You can make prediction on synchronization of oscillator placed on structure which are in the real-world network. So I don't know how much time I used because I didn't check my but it's almost okay. So I thank you a lot for your attention. And I ask you to submit your best paper to chaos orders and fractals. We have a rule this year that we allow maximum 5 papers per author per year. So really, we want you have the best 5 papers of yours. Chaos orders and fractal became the best and most prestigious venue in nonlinear dynamics and statistical physics. The impact factor last year was 3.764, and this year it's even larger. So very soon there will be the release of the impact factor, and we will have a very nice surprise. So thank you a lot. I am open to discussion. Hello?
I was without sound. So thanks a lot, Stefan, for the wonderful talk. I think there are questions from the audience. So please use your time. No questions.
No questions. So when there is no questions, it means nobody understood.
No, it was too clear.
No.
Too obvious.
No, okay, but no, in general, I'm very proud of this result that because it's really an extension. I mean, it allows you to make prediction. Of course, the main limitation of the master stability function is that it considers identical systems. So that's the main limitation, because the approximation you do since the very beginning is that all the systems are equal. And in nature, you don't have, such a situation. But on the other hand, it's extremely elegant. It allows immediately to tell you which are the structure through which this dynamical system synchronize in a way, in another. So you make a lot of predictions.